Hello students, welcome to this lecture on the data path subsystems where we will focus on the carry skip adder. Right, so we had seen earlier the carry ripple adder. Here we will see, take a look at the carry skip adder. We will try to utilize the same propagate and generate signals, of course the group wise propagate and generate signals, and then try to design this carry skip adder, which turns out to be a little bit faster than that of the carry ripple adder. Right, so let's begin with this. So what we had seen is the carry ripple adder. So let me take the pointer, the carry ripple adder. Here, the way we have utilized the group generate signals is, G1 is to 0, we generated from G0 is to 0. And then from 1 is to 0, we generated G2 is to 0. And then similarly, we generated G15 is to 0 for a 16-bit adder circuit. Right. So the carry skip adder is nothing but it uses the same the group generate signals, but it also utilizes the group propagate signals and then tries to shorten the critical path. Right. So if you remember the carry ripple adder, the critical path for generating the S16 was coming from all the the group generate blocks, 15 block, 14 block, 13 block, all the way from one block. Right, here we'll try to shorten the critical path by generating the group propagate signals, or by utilizing the group propagate signals. In the carry ripple addition, we have not actually utilized the group propagating signals. The propagate part was still a bitwise propagate signals. Here we'll try to utilize the group propagating signals to shorten the critical path. And how are we going to do that? So we'll write the expression for a 16-bit addition. We will try to find out G4 is to 1. We'll try to find out 8 is to 5. Right? We'll try to find out 12 is to 9. We'll try to find out the 16 is to 13. Right? Once we have all these things, the group of 4 bits. So we have done 4 groups of each individual groups having 4 bits. Once we have that, then we will try to extract G4 is to 0, G8 is to 0, G12 is to 0, and G16 is to 0. Right, and then utilize or use this 4 is to 0, 8 is to 0, 12 is to 0, and 16 is to 0 to extract the sum bits. Right. So let's try to understand how we are going to generate this 4 is to 0. So that's what I have written here. 4 is to 1 here is nothing but G4 is to 4 plus P4 is to 4, G3 is to 1. G3 is to 1 is nothing but, created from G2 is to 1. G2 is to 1 is created from G1 is to 1. Right? And once I have G4 is to 1, I should be able to generate, the 4 is to 0 from G4 is to 1 plus P4 is to 1, G0 is to 0. All right. So remember that in a carry ripple adder, the way we generated 4 is to 0 was G4 is to 0 was nothing but G4 plus the bit level P4 ending with that of 3 is to 0. Here, the way we are generating it is different. G4 is to 0 is G4 is to 1 that has been generated, and P4 is to 1, and then G0 is to 0. So here in the carry ripple addition, we have taken K is nothing but equal to I for the 4th bit, 8th bit, 12th bit, and then the 16-bit group generate signals. Here for the 4th bit, 4 is to 0, or the 8 is to 0, or the 12 is to 0, or the 16 is to 0, we have taken K value, right? In this case, the K value is nothing but 1. Right, in the subsequent G8 is to 0, we will take the K value to be 5, and for 12 is to 0, we will take K is equal to 9, and then for the 16 is to 0, we will take the K to be nothing but 15. Rather, 16 is to 0, we will take the K value to be nothing but 13. Right, so what we have done is we have utilized a different K values, right, and then try to generate this group generate signals. Right, so we have now utilized the group propagating signals in this case, and then try to represent G4 is to 0 in a different manner. Right, although for a 4-bit addition we may not be able to see the impact of this particular design. Let's try to see for a 16-bit addition how it can be impactful, right? So for a 16-bit addition, what we are trying to do is we are trying to generate 4:1 signal, right? We are trying to generate 8:5. We are trying to generate 12:9 and 16:13 signals simultaneously. So what it means is simultaneously means is 4:1 depends on 3:1, 3:1 depends on 2:1, 2:1 depends on 1:1, right? So if I have a group of 16 bits starting from 1 to 16, we are going to divide, or we are going to take it logically divided into 4 such groups, right? 1:4, 5:8, and then 9:12, and then 13:16. So 4 groups are generated, and simultaneously, this is going to give me G4:1. This is going to give us G8:5. This is going to give us G12:9, and then this is going to give us G16:13. Right? So G4:1 depends only on G3:1, and then it's the bit level 4 and propagate bit level 4 bit, and 3:1 depends on G3:3, and then P3:3, G2:1, and then so on, right? So all this individual groups of 4 bits can be simultaneously be generated, and that doesn't have to depend on the other groups. So this doesn't have to depend on 8:5, or 8:5 doesn't have to depend on the 4:1. 12:9 doesn't have to depend on 8:5. 16:13 doesn't have to depend on 12:9, right? So if I can actually logically divide into the 4 groups, then individual groups can simultaneously generate 16:13, 12:9, 8:5, and 4:1 signals. Once I have that, G4:1, 8:5, 12:9, and 16:13, then we can actually generate G4:0, 8:0, 12:0, 16:0 by using this group propagate signals 4:1 from G0:0. Once this G4:0 is generated, we can utilize it for the next one, G4:0, to generate 8:0. Once 8:0 is there, then we can utilize it for generating 12:0. 12:0, if it is there, then you can utilize it to generate 16:0. But notice that all this 4:1 to 16:13 are generated simultaneously. It doesn't have to wait for the previous, the group generate of the lower bits, right? All these things can be generated simultaneously, right? So that's what I'm writing down simultaneously, and doesn't have to wait, right? Once this is available, in fact, this P4:1, 8:5, 16:13 can also be generated simultaneously. So this is also generated simultaneously. Once this is done, both of them are available, and it's just waiting for the group 0:0 or 4:0 or 8:0 or 12:0 generate bits, right? So once these two are available, with this is also being available at the same time, it takes one OR gate and then an AND gate to generate 4:0. 4:0, if it is generated, then it takes one OR gate and one AND gate to generate 8:0, and then so on, right? So what it means is it actually skips 8:0, can actually skip, right, generating 7:0 or 6:0 or 5:0. In fact, if 4:0 is made available, it can directly generate 8:0. 12:0 can actually skip G11:0, 10:0, and 9:0. In fact, whenever the G8:0 is made available with one AND and one OR gate, it should be able to generate 12:0. G16:0, doesn't have to wait for G15:0, 14:0, 13:0. The moment 12:0 is available, it can generate a G16:0. Right, so it skips G15:0, 14:0, and 13:0, and directly whenever 12:0 is made available, it then directly generates a G16:0. So to visualize, right, let's try to rewrite this expression. So I'm taking the G4:1, right? So just, if I want to express G4:1, it is nothing but G4:4 plus P4:4 and that of G3:1. 3 is to 1 is generated from G2 is to 1. 2 is to 1 is generated from G2 is to 2 or or this one, right? It has to depend on G1 is to 1, right? So what it means is if I look into this particular expression, right, what it says is if I want to get G4 is to 1 as 1, right, then either G4 is to 4 has to be 1, or G3 is to 3 has to be 1, or G2 is to 2 has to be 1, right? Or else G1 is to 1 has to be 1 and P2 is to 2 has to be 1, P3 is to 3 has to be 1, P4 is to 4 has to be 1, and then thereby I'll get a G4 is to 1 as 1. Now if I look into this G4 is to 1 as 1, or if let's say G4 is to 4 as 1 in this case, so that I'll be able to generate G4 is to 1. The moment the G4 is to 4 is 1, that means that my A4 and ANDing with that of B4 has to be 1. Right? That means A4 and B4 bit are 1. So in that sense, my P4 bit has to be 0. Right? The XOR operation of both the bits are 1. So my P4 has to be 0. So that means my P4 is to 1 is actually 0 now. Right? P4 is to 1 is nothing but the XOR operations of all P4, P3, P2 and P1. All right, so in that sense, it has to be 0. Right. So, so if I consider this G4 is to 1 as to be 1, and if it is 1 because of this, the individual generate bits, G4, G3, G2, right, then my P4 is to 1 will become 0. All right. So that's what I am implying. If G4 is to 1 is 1, implies that G4 or G3 or G2, or in this case G1 has to be 1. If G1 has to be 1, right, even in that case P1 will be 0. So P4 is to 1 will actually be 0. Right, so that's what I have written. Moving ahead. So what I'm doing is, if G4 is to 1 is actually 1, we know that P4 is to 1 will be definitely be 0, right? So if that is 0, I can actually take P4 is to 1. I can virtually represent this particular expression as P4 is to 1 and then the complement of that with that of G4 is to 1 plus P4 is, or rather or it is not plus, it is an or expression of P4 is to 1 and G0 is to 0, right? So if G0 is to 0, or rather G4 is to 1 is 0, then P4 is to 1 can be 1 or 0, right? So it still depends on P4 is to 1 whether it could be 0 or 1, right? So G4 is to 0, if it is G4 is to 1 is 0, then it depends on P4 is to 1. If it is 0 or 1, it can pass G0 is to 0 to 4 is to 1, right? If G4 is to 1 is actually 1, then we know that P4 is to 1 is definitely 0, right? So I can use this particular complement expression without having any change in the logical expression of this, right? Now, if suppose I use this particular expression for designing my circuit, so this I'm going to use it to design my circuits, right? How am I going to do that? So we can utilize this P4 is to 1, P4 is to 1, the complement of that, right? Use it as a select line for a multiplexer, and then pass the two inputs of G0 is to 0 and 4 is to 1. So G0 is to 0 and 4 is to 1. If P4 is to 1, the select line is 1, then I will pass the G0 is to 0 at the output. If P4 is to 0, 4 is to 1 is actually 0, then I will pass G4 is to 1 to the output of the multiplexer. So this is very important to understand that once I have the group propagating signals, P4 is to 1 or whether it is 1 or 0, right? It just passes, let's say that if it is 0 in this case, right, it will pass G4 is to 1 to the G4 is to 0 output, right? If it is 1 here, right, then it passes G0 is to 0 into the G4 is to 0, right? Similarly, if I have P8 is to 5, right, simultaneously generated when P4 is to 1 is generated, and if it is 1 here, it will pass this 4 is to 0 to the output here as G8 is to 0, right? And similarly, if I have 12 is to 9 as 1 here, it will pass G8 is to 0 to the next output of the multiplexer, right? So the moment P4 is to 1, P8 is to 5, P12 is to 9 is 1, it can actually skip, right? It will actually skip generating, or the G4 is to 1. It will directly take the output from G0 is to 0. This will go as 8 is to 0. This will go as 12 is to 0. So it can actually skip generating the intermediate generate signals because of the multiplexers. And that's why it is called as the carry skip adder. To put this particular multiplexer block into the reality, so we have two blocks now. One is generating P4 is to 1 from A4 is to individual A and B input bits, individual A and B input bits, right? So for an 8-bit addition here, we have created two such blocks. One is generating P4 is to 1, the other one is generating P8 is to 5, which will go into the select line of the multiplexers, right? And on the lower side, we have two blocks. One is generating G4 is to 1, another one is generating 8 is to 5. So that is been provided, that is fed to the one input of the multiplexer, The other input of the multiplexer is coming from G8 0 is to 0, and output is G4 is to 0, which will go into the this particular multiplexer input, right? So the moment G4 is to 1 is 1 here, G4 is to 0 will be G0 is to 0. It doesn't have to wait for this to be computed. All right. And similarly, P8 is to 5, if it is 1 here, G4 is to 0, which is nothing but G0 is to 0, will be passed to the G8 is to 0. Doesn't have to wait for G8 is to 5 to be computed. All right. And this particular block, I've said that it is going to generate the sum bits S4 is to 1. That means S4, S3, S2, S1. And then this particular block is going to generate S8, S7, S6, S5. Right? So the this particular multiplexer is going to skip the carry out that is being generated. Carry out in the sense, if I want to generate G8 is to 0, it actually skips G7 is to skips the generation of G7 is to 0, 6 is to 0, 5 is to 0. It directly takes G4 is to 0 or G8 is to 5 based on the group propagate signals, right? So it may not be advantageous if I have only 4-bit of addition, but it will be advantageous if I have a higher order adder subsystem block design, right? 16-bit addition or 32-bit addition, it will directly skip producing, the 32 for the 32-bit addition, it will directly skip producing 30 is to 0 or 29 is to 0. It can actually take, if the last group is 1, it can directly skip the generate signals, and then they directly take the 28 is to 0, which is actually taken from 24 is to 0, and actually taken from 20 is to 0, and then so on, right? So this particular the carry input of 0 is to 0 can actually be passed to the last bit addition, right? So using this, can we now design the PG architecture, the propagate and generate architecture? And the first level is nothing but the bitwise. The second one is the groupwise, where it will generate the groupwise generate and groupwise propagate bits in this carry skip adder. And then the third one is the sum bits generation, right? So in the first bit, what we are assuming is that I have not indicated any of the OR, or rather the AND and the XOR gates here. What it means is the XOR and the AND gates are there, and it is giving us the bitwise generate and then the propagate signals. So 1, 2, 3, 4 up till 16 represents the bitwise generate and then the propagate signals. The 0 is grounded, represents that the carry input is 0 here. So this represents 0 is to 0, which will be nothing but G0, which is nothing but C0, or we can also say that it is seen to be nothing but 0. All right. And this individual blocks here, blocks here, blocks here, blocks here, is going to generate the group wise generate and propagate signals. So this particular 8 to 5, 12 to 9, 16 to 13 is going to give me 16 is to 13. It could be G 16 is to 13 and P 16 is to 13. Here 12 is to 9. The output here represents generate G 12 is to 9 and P 12 is to 9. Similarly, 8 is to 5 will give me G 12 is to 9 and P 12, 8 is to 5, P 8 is to 5 and G 8 is to 5, and this 4 is to 1 is going to generate G 4 is to 1 and P 4 is to 1, right? So this one, all these three blocks are at the same level, indicates that all of them, all the three blocks here, all right, which is nothing but an AND and OR blocks, and the XOR operations to generate the propagate signals is are there parallelly. So this block doesn't have to depend on any of the output of this particular group blocks, and then this particular group block doesn't have to wait for this particular group of blocks, and then so on. So that's why it is kind of an independent, and all of them, if all the signals A16 to A1 and B16 to B1 are made available, all the output of these blocks are generated simultaneously, right? So once they're available simultaneously, so this particular line which goes to the multiplexer here, the multiplexer takes three inputs. One is coming from 0 is to 0. The other one is G4 is to 1. And then the third one, the select line, is nothing but P4 is to 1. So based on the select line, it will pass the output, whether it is coming from this one or the generate G4 is to 1. And then it is going to produce 4 is to 0. This 4 is to 0 is going to this particular multiplexer, the next group, higher order group multiplexer, where this particular line indicates two inputs. Again, one is the select line, the other one is G8 is to 5. The second input is G4 is to 0. So based on P8 is to 5, we will get 8 is to 0, whether it is coming from 4 is to 0 or whether it is coming from G8 is to 5. This particular multiplexer output will go to this particular multiplexer input, and then this particular line, again two inputs, one is the select line, another one is G12 is to 9. And finally, for a 16-bit addition, we will have the fourth multiplexer. One input is coming from 12 is to 0, and then the other line, which will have one as a select line, the other one as G16 is to 13. The output is going to be G16 is to 0, right? So with this set of three, the simultaneous blocks here, and then this multiplexers, we are going to get 16 is to 0, 12 is to 0, 8 is to 0, 4 is to 0 really, really fast, right? Because it is going to skip generating 3 is to 0 or 7 is to 0 to 11 is to 0 or 15 is to 0 and directly get the 16 is to 0 from the 12 is to 0 block, from the 8 is to 0 block, from the 4 is to 0 block. All right. But here the other, we still need to extract the sum bits, right? We still need S2, S3, S4. 0 is to 0 is going to give me S1 because 0 is to 0 with that of the P1 XOR will give me the S1. And P1 is anyways available here, right? S2 will require the P2 signal that is available here with that of 1 is to 0. All right. So I need somehow get the 1 is to 0 block. So 1 is to 0 block, I can actually have this particular square block, which is nothing but AND and OR block. This square block is also AND and OR block. So AND and OR block with this one, G1, P1, and G0 is to 0 is going to generate 1 is to 0 here, right? And this block can be along the same level of this particular blocks, right? The reason is it doesn't depend on this particular block at all, right? It has to take the G1, P1 signal coming from here and then G0 is to 0. The second block here has to wait for 1 is to 0 and then it will generate 2 is to 0. And then this block will generate 3 is to 0. All right. So this one will give me 3 is to 0, 2 is to 0, and 1 is to 0 so that I can produce or extract sum 4, sum 3, sum 2. Right. Similarly, for the other group, 8 is to 5, we have got 8 is to 0 here, but I need 7 is to 0, I need 6 is to 0, 5 is to 0 so that I can produce S8, sum 8, sum 7, sum 6. So I will produce these three blocks here of AND and OR gates. And this first block will wait for 4 is to 0 whenever the output of the multiplexer. At the same time, the output of this multiplexer will go to the another multiplexer, but at the same time it will also go into the AND and OR block here. So the AND and OR block here, once it produces 5 is to 0, it will go into the next block, which will give me 6 is to 0, and then the next block, which will give me 7 is to 0. Similarly, I will complete for the other two groups, generating 9 is to 0, 10 is to 0, and then 11 is to 0, and then the last one, the last group, I'll have 13 is to 0, 14 is to 0, and then 15 is to 0. All right. So notice that we have multiplexers, and then this set of three blocks here with the multiplexers is going to give me 16 is to 0, 12 is to 0, 8 is to 0, and 4 is to 0. Only this particular blocks, which are which are marked in the black lines here, are going to give me the output of 3 is to 0, 2 is to 0, and 1 is to 0. So within the individual bits, its inner the group generate bits are generated by this black lines boxes, and all these square boxes are nothing but AND and OR gate representation. The multiplexer is a different one, right? So once I have this 3 is to 0, 2 is to 0, 1 is to 0, and then 7 is to 0 to 5 is to 0, and 11 is to 0 to 9 is to 0, and then 15 is to 0 to 13 is to 0, I can then produce the sum bits of all this 16 adder outputs. All right. So what should be the delay here? So the delay here is considered for the critical path. The critical path is still generating the S16 bit, starting from the first bit A1, B1 available. So I will have a delay from this particular first stage, which is nothing but the bitwise generate and propagate signals, the delay due to that. The second one, I will have to find the critical path here. And then the third one, which will be nothing but the XOR operation. So I know the bitwise delay, bitwise PG delay, and then the XOR delay here. The second one we'll have to find out. It turns out that the delay is due to this three multiplexer outputs. So the multiplexer for this particular group, the multiplexer for the second group here, the multiplexer for the third group, and then this is made available for this black boxes so as to generate 15 is to 0. Right, and then generate the X16, right? So my critical path here in the second group will be like this, right? And then the this three black boxes doesn't have to doesn't give any inputs to this multiplexer. So the multiplexer either gets the input here or it is getting the input here, right? So from this block, which is waiting for this block, and then this block, and then this one. So my critical input, or rather the critical path, which is going to give me the delay expression for this carry skip adder, starting from the C input or whenever the inputs are available to S16 output, is nothing but this delay of these three boxes plus these three multiplexers, and then finally these three black boxes, right? And plus of course the XOR gate, and then the PG in the first level, in the first stage, the bitwise propagate and generate signals delay, right? So in a sense, the carry skip adder, right? The carry skip adder, the delay of that for generating the S16 bit is nothing but the first stage bitwise propagate and generate signals, the XOR gates for the final third stage. So this is the first stage, this is the third stage, and in between I will have to have the first three blocks, right? The first group, and then the last group, the black boxes, TAO and an OR gates, the first group, TAO and an OR gates, and then in between the three multiplexers delay, right? In fact, if I can actually do, all these are three blocks because we have four groups and each groups are of 4 bits. So if I can actually make K groups, I can actually make an asymmetric groups, asymmetric in the sense, the groups having different bits, or rather, I can have K groups. If there's a 20-bit addition, then I can have 5 groups of 4 bits each, right? So not really asymmetric, but 5 groups with 4 bits each. So k is 5 here and n is equal to 4. So then I can have k, this could be represented as k minus 1 number of multiplexers delay plus this TAO, and then this TAO will make it 2 times n minus 1 TAO, right? So 4 bits, 4 minus 1, 3 into 2, and then the number of groups will be k groups, right? So if I consider this particular delay and then compare with that of the carry ripple adder delay, it will be same TPG of bitwise, right? And it will be having the same T XOR in the third stage plus, but here it will be for an n bit, right? So k into n will give me the total number of additions. So k n minus k minus 1 of TAO will be my answer for the carry ripple adder. Whereas here it is nothing but 2 into n minus 1 into TAO plus k minus 1 into TMUX. And this carry skip adder is likely to be faster than that of the carry ripple adder.